Welcome to the Deep Dive. Today, we're strapping in and taking a journey back in time,
Right.
specifically to the mid-1960s, to explore space. Well, not as we know it now, but as it was dreamed about back then.
That's right. Our source for this is, it's really quite fascinating. It's this little book from 1964 called Exploring Space, a Ladybird Achievements book.
The Ladybird book. Okay.
Yeah, and it gives us a great shortcut, to understanding that specific perspective right on the cusp of some huge space milestones.
And our mission today is really to unpack what people understood, what they were guessing about, and honestly, what might have surprised them from that 1964 viewpoint. So get ready for some insights that might seem obvious now, but were pretty revolutionary, maybe even mysterious back then.
Definitely.
Okay, let's dive in. How did people even start thinking about reaching for the stars in the first place? Like way back?
Well, the book takes us right back there. It reminds us that the dream of flying, of space travel, it's not new at all. It goes back centuries, woven into myths and stories long before the science actually caught up.
Yeah, it even mentions classic fiction like Jules Verne's From the Earth to the Moon.
Right.
Where they get there by being shot out of a giant gun.
Yeah.
Can you even imagine? That sounds like a truly awful way to commute.
It really does. It just shows how boundless the imagination was. But turning that dream into reality, that needed some real physics, as the book explains.
Right.
The basic idea of how rockets actually work, which the book describes, it's surprisingly straightforward when you break it down.
And it is pretty simple. You burn fuel inside the rocket.
Yep.
That burning fuel creates hot gas. The gas expands like crazy, and it shoots out a nozzle at the back.
And that shooting out, that's the key action. Because, Sir Isaac Newton figured this out ages ago. For every action, there's an equal and opposite reaction.
Newton's third law.
Exactly. The book makes it relatable, too. It's the same thing when you push a wall, or your feet push the floor to walk, or even the kick from a rifle. That gas pushing backward pushes the rocket forward. Simple as that, really.
That connection makes perfect sense. But here's where it gets tricky for actually doing it. What exactly fuels the rocket? The source clarifies you need two main things.
Right. You need the fuel itself, obviously. But the crucial bit is you also need something to let that fuel burn.
Like oxygen.
Exactly. Here on Earth, we just use the air.
No.
But space, well, space is a vacuum, no air. So you have to carry your own oxygen or oxidizer.
Right, the oxidizer. The book mentions a couple of combos they were using or thinking about then. Alcohol with liquid oxygen.
And hydrogen peroxide was another one mentioned. And carrying all that oxidizer, that's a huge part of the weight challenge.
And that explains, I guess, the next thing the book talks about. The sheer scale. Why were these rockets just so enormous?
Yeah, the book really tries to give a sense of scale. Compares them to familiar things. It says they could be as tall as a big building, like St. Paul's Cathedral.
St. Paul's. Wow. Thinking about that size in 1964.
Yeah.
It must have seemed absolutely colossal.
Totally. And the book points out something amazing about the weight. The fuel needed is vastly, vastly more than the empty rocket itself.
Really?
Yeah, we're talking hundreds of tons just for the fuel and oxidizer, while the rocket structure might only be, say, 12 tons when it's empty.
Hundreds of tons of fuel just to lift 12 tons of rocket plus whatever's inside. That ratio is just wild. So how did they even manage to get all that off the ground and into space?
Yeah.
Especially something like a satellite.
Well, that's where multi-stage rockets come in, as the book shows. It illustrates a typical three-stage design.
Okay.
Each stage basically has its own engine, its own fuel tanks, its own oxidizer. The idea is the first stage fires, gets things going, then drops away when it's empty, makes the whole thing lighter for the next stage.
Shedding weight as you go.
Yeah.
Smart, like throwing off ballast.
Pretty much. And the launch itself, the book really captures the drama of it.
I bet.
It talks about months of prep, the tension of the countdown, and then just this huge burst of flame and roar.
Wow.
It says the rocket moves kind of slowly at first and just tears away, becoming this tiny, white, fiery speck heading for the stars. Must have been incredible to see.
Absolutely. So all that power, all those stages, what does it actually take to get into orbit around Earth? We talk miles on Earth, but the book really hammers home how vast space is, even just nearby.
Oh, yeah. It gives those numbers that just blow your mind. Earth to sun, 92.9 million miles. Earth to moon, nearly 240,000 miles. Even Venus and Mars, our neighbors, are tens of millions of miles away when they're closest.
And the stars are. Just forget it.
Exactly. Proxima Centauri, the nearest one after our sun, millions and millions of miles. The scale is just immense.
Mind-boggling. And yet, incredibly, by '64, when this book came out, they had managed orbit. The book marks that specific date, October 4th, 1957.
Yep, that was Sputnik 1, the first artificial satellite launched by Russian scientists. The book notes it weighed 184 pounds. Tiny compared to the rocket needed.
Right.
And it mentions that many more had followed by the time the book was written.
Okay, so Sputnik's up there. But what actually keeps a satellite going round the Earth? It's not just floating randomly, is it?
Not at all. And this is one of the coolest physics bits the book explains simply. It's all about balance.
Balance.
Yeah, Earth's gravity is constantly pulling the satellite down, right? But at the same time, its speed, its forward motion, is trying to make it fly off in a straight line outwards.
Okay.
The book uses that great analogy of swinging a stone on a string. The string pulls the stone in, that's like gravity. But the stone's speed keeps it swinging around instead of just falling straight to your hand. That's like orbital motion.
That's a brilliant analogy. Really makes it click. They're clearly trying to make these new ideas understandable. So if the balance is key, what happens if the speed isn't quite right?
Well, the book explains that too. If you launch too slow, gravity wins. The string breaks, basically, and the satellite falls back, burns up in the atmosphere.
Right.
If you launch too fast, the outward force is too strong. It overcomes gravity, breaks free from Earth, and just zooms off into deep space, lost forever.
So there's a sweet spot, a Goldilocks speed. And the book gives that speed for an orbit just a few hundred miles up. Must have sounded incredibly fast back then.
About 18,000 miles an hour.
18,000 miles an hour.
Yeah, that phenomenal speed is what you need to constantly balance Earth's pull and stay in orbit.
All right, so you've launched, you're in space, maybe orbiting, maybe heading somewhere specific. How do you actually steer the thing? You can't just like turn a wheel.
Exactly. The book points out, rudders need air or water to push against. Useless in space, so they needed different methods. It talks about two main ways they were thinking about or using then.
Okay, what's the first?
One way is using a vane, basically just a small metal piece, stuck right into the stream of hot exhaust gas from the engine. By tilting that vane, you deflect the gas stream. And Newton again, push the gas sideways, the rocket gets pushed the opposite way.
Pushing against your own exhaust.
Yeah.
That's really clever. Okay, what's the other way?
The other method is using small separate combustion chambers, like tiny extra rocket engines mounted on the spacecraft.
Thrusters.
Exactly, thrusters. Firing these in short bursts gives you precise little pushes, sideways, or what you might think of as up or down. Though, as the book rightly notes, up and down don't really mean much out there relative to Earth once you're away from it.
Right. Got to ditch those Earth-based ideas. Okay, so you can steer. The next big target the book discusses is, naturally, the moon. How long did they reckon that trip would take in '64?
The book suggests about 3 or 4 days, and it paints this amazing picture of the view as you leave Earth.
Yeah.
Seeing the land and sea shrink below, the clouds falling away, the sky getting darker and darker blue, until Earth is just this distant, beautiful ball with green and brown patches and white ice caps.
Wow. Just imagining that view in 1964. Incredible. And as you get closer to the moon, the gravity situation changes, right?
Precisely. As you leave Earth, its pull gets weaker. As you near the moon, its gravity starts to take over. But the book points out the moon's gravity is much weaker than Earth's.
How much weaker?
Only about 1/6 as strong. Because it's just got much less mass, it's smaller.
And that's why they give that classic example. If you weigh 12 stone on Earth, you'd only weigh 2 stone on the moon.
Exactly. That really hits home, doesn't it? Imagining how different moving around would feel. Bouncing.
Totally. The book also mentions the discussion around actually going to the moon back then. Not everyone was on board.
No, it notes some people thought it was a huge waste of money and effort. Just folly. But others saw it as this massive, tremendous achievement, comparing it to the first airplanes or even Columbus discovering America.
Interesting that the debate was already happening. So based on the spacecraft photos they had, by then they'd seen the far side, right, and instruments. What did the book say they knew about the moon's surface in '64?
Yeah. They knew it was incredibly cold. Frozen in intense cold is the phrase used.
Sure.
They knew there was no air, which made life, as we know it, pretty unlikely. And without air, the night sky would be perfectly black, stars shining brilliantly, no twinkling.
And the surface itself, what did it look like?
Covered in thousands of craters, big and small, just scattered everywhere. But here's where the mystery really kicked in for them. The book highlights things they didn't know.
Like what?
Well, questions about the soil, the rock. Was it covered in a deep layer of fine dust? Could a spacecraft actually sink into it?
Ooh, yeah, that's a worry.
And what about those weird bright white rays you see spreading out from some craters, like lines on a peeled orange, the book says? What were they? These were genuine unknowns back then. So moving from just exploring the moon to maybe living there, the book actually considers setting up a moon base.
A moon base. And interestingly, it suggests a moon base might be, quote, better than a space station orbiting Earth, even though the moon's much further away. Why was that?
Well, the book seems to imply the moon offers, like, a more stable, permanent platform compared to something constantly orbiting. Yeah. It also notes the unique environment. No twinkling stars, remember, and that really extreme day-night cycle. 14 Earth days of constant sun, then 14 days of deep freeze night because the moon rotates so slowly.
14 days of night. That would be challenging. And living there, you'd have to bring everything, right? Food, water, air.
Absolutely everything. The book really stresses this. It kind of floats the idea that maybe oxygen is mixed in the rocks there, but then immediately says, look, all the oxygen in Earth's atmosphere is needed right here.
Good point.
It even mentions growing crops, potentially, in sealed greenhouses, using minerals dissolved in water, a very early concept of, lunar farming.
That shows they were already thinking long-term survival.
Yeah.
Okay, beyond the moon, the book looks further out to other planets. What did they know or guess about them in 64?
Well, it describes Mercury, closest to the sun, as just too extreme. Roasting hot on one side, freezing cold on the other. Very unfriendly.
Makes sense.
Venus is described as much bigger, similar size to Earth, actually, and super bright in our sky because it's totally covered in thick clouds.
The clouds.
And crucially, the book notes that in 1964, they couldn't see through those clouds. They didn't even know how fast Venus rotated. That's a huge difference from what we know today.
Wow, they couldn't tell how fast it spun? That really highlights the gaps back then. And Mars, the red planet.
Mars was known to be much further away than Venus, and it was the big focus for speculation about life, which the book gets into a bit later. And then beyond the planets, the stars. The book reminds us our sun is just one star, an average one, really.
Among countless others.
Yeah.
And the distances. Just astronomical. Literally, it mentions Proxima Centauri again, the next closest star, millions of miles away.
Yeah, and light from it takes over 4 years to reach us. Sirius, the brightest star we see, much further still. Travel to the stars, the book admits, would be a very long journey, needing speeds close to light speed.
Which, yeah, their rockets couldn't do. But the book makes this really interesting, kind of counterintuitive point about the energy needed for interstellar travel versus planetary travel.
It does. It suggests it would take very little more energy to send a ship to a star than to one of the planets. Now, that sounds bonkers, right? Stars are so much further.
Yeah, how does that work?
I think the book's point is about the initial big hurdle, escaping Earth's gravity and atmosphere. That takes the vast majority of the energy. Once you're out there and going really fast, adding more speed while still needing tons of energy is maybe little more compared to that enormous first step of getting free. Reaching light speed is another matter entirely, of course.
That's a fascinating way to think about it from that time. Okay, back closer to home. The book discusses actually living in space itself. What kind of structures did they imagine?
One big idea presented is a space station shaped like a giant wheel. Hundreds of feet across, maybe.
A wheel? Why a wheel?
The key thing was it would spin, it would revolve. That rotation creates centrifugal force, which would push people outwards, simulating gravity inside, so you wouldn't just be floating around all the time.
Artificial gravity from spinning. Makes sense for long stays.
Exactly. These wheel stations were imagined orbiting Earth, acting like floating aerodromes, the book says. Places for ships to dock, refuel, maybe get fixed, without coming all the way back down to Earth.
Like orbital pit stops.
Pretty much. The book admits they'd be hard to build, but could house people for weeks or months, maybe serve lots of long-term purposes.
And speaking of things orbiting Earth, the book highlights the satellites that had already gone up since Sputnik. How are they already proving useful by 64?
Well, it points out their value for communication, especially radio waves. Radio travels straight, right? So getting signals around the curved Earth is tricky.
Yeah, the horizon gets in the way.
But satellites high up could act like mirrors in the sky, bouncing signals like TV pictures across oceans and continents.
Early global comms. Cool. What else?
Weather satellites were a big one already. The book mentions the Tiro series, says they'd already spotted over 50 storms. Huge for tracking typhoons, watching cloud patterns globally.
That's genuinely useful stuff.
Yeah, and satellites were also looking out into space, measuring things like air temperature high up, Earth's magnetism, gravity variations. The book ends that bit with a hope, actually,
What's that?
that these powerful new tools would be used for peace, not for war. But of course, space wasn't seen as perfectly safe. The book does address some key dangers.
Right, our atmosphere shields us from a lot. What were the main worries out there, according to the book?
Well, one big one was radiation. Dangerous rays from the sun, like ultraviolet and cosmic rays from deep space. Outside the atmosphere's protection, you'd need shielding on the spacecraft. Thin layers of metal, glass, whatever.
Okay, radiation shielding. Makes sense. What about, like, physical stuff floating around?
Meteors. That was another major concern. Tiny bits of dust, stone, metal, just whizzing through space incredibly fast.
Micrometeoroids.
Exactly. On Earth, they mostly burn up harmlessly as shooting stars. But in space, there's no air to slow them down or burn them up. Even a tiny speck hitting a spacecraft at thousands of miles an hour could cause serious damage.
Yeah, that's a bit scary. Like cosmic bullets. Finally, the book touches on that ultimate question. Life on other worlds. What's the 1964 take on that?
Well, it mentions the old idea about Mars, intelligent beings, maybe they built canals.
Kardashian canals, right.
But importantly, even in 1964, the book is pretty clear. It calls it a most interesting idea, but says it's unlikely to be true based on what they knew then.
So already moving past the more fanciful sci-fi ideas about Mars, what about other places?
Well, Mercury and Venus, as we heard, seemed way too extreme for life. Too hot, too cold, maybe wrong atmosphere. But then the book looks further out, towards planets orbiting other stars. Exoplanets, we'd call them now.
And the sheer numbers involved.
The
book mentions those, right?
Oh, yeah. It points out our Milky Way galaxy alone has maybe 100,000 million suns, 100 billion. And the book does this little calculation. Even if only 1 in a million of those suns had planets, that would still mean potentially many thousands of other worlds out there.
Thousands just from that tiny fraction.
Worlds that could be like ours, it suggests, or maybe worlds with life totally different from anything we can imagine.
That sense of possibility, even with those conservative numbers, is really powerful.
Mm-hmm.
And the book connects this to something fundamental, doesn't it? About what everything's made of.
It does. It finds it really fascinating that the basic stuff, the elements that make up our world, our bodies, well, scientists were seeing those same elements everywhere they looked in the universe, in distant stars and nebulae.
The same building blocks are everywhere.
Yeah, that shared cosmic chemistry kind of lends weight to the idea that maybe, just maybe, life isn't unique to Earth.
So we've just taken a proper deep dive into space exploration as people saw it, or were starting to see it, through the lens of that 1964 Lady Bird book. It's really amazing to see the science, the engineering challenges, the hopes, the genuine question marks from that time.
Absolutely. We've gone from, the basic physics of rockets and getting into orbit to how you'd even steer out there, the mysteries still surrounding the moon, early ideas about living in space, even touching on life elsewhere, all based on what they understood right then, mid-60s.
And it really gives you this profound appreciation for how far we've actually come since then, but also how much of the groundwork, the core ideas, the sheer imagination was already firing on all cylinders back then. So consider this thought, maybe a provocative one, that comes straight out of the book's perspective. You hear those staggering numbers, 100 billion suns in our galaxy. The book wonders about planets, maybe thousands, maybe more. And you know that the very stuff that makes you up, the carbon, the oxygen, the iron, it's everywhere out there.
Yeah.
Does knowing the building blocks are universal, make the idea of other worlds with life feel more likely to you? Or do the immense distances, the dangers the book outlined, make it still feel incredibly remote? Something to perhaps mull over next time you look up at that vast star-filled night sky.